Hi, welcome to this lesson of linear algebra. So we are at the point where we're going to talk about linear transformations. Okay, so let's go through some definitions and solve some examples. All right, so let V and W be vector spaces over a field F. We've gone through vector spaces, so at this point, I hope that you know what a vector space is. A linear transformation from V, right, to W is a map, and it takes some values in V and then map them to some values in W. Okay, such that the following are satisfied. So the transformation, the rule that you are using for the transformation, so you can think of this as mapping. The rule for the particular mapping is defined to be T, such that if you take the T, if you apply it on the summation of two vectors in V, it will be the same as taking the transformations individually and then adding them. So when you take the transformation of T of x plus y is the same as T of x plus T of y. What it means is if you sum these vectors x and y in V and then you take their transformation, the transformation of the summation is the same thing as taking the transformation of x individually or independently and taking the transformation of y independently and then you add them, right? That's what it is trying to say. And also, if you multiply any vector in V by some scalar in the field and you take the transformation, whatever result you get here should be the same as taking the transformation of the original vector x before you multiply whatever result you got by the scalar. So T of a times x should be equal to a times T of a. So a times T of x, sorry. So these two things should be satisfied in order for our transformation to be linear transformation. So a linear transformation satisfies these two things. I mean, some books will combine these two things or these two conditions and say that it satisfies something like this. Y should be equal to a T of x plus T of y. Remember, you can combine these two conditions as one like this, okay? But we are going to do them separately, and when you are more confident about understanding these two things, then you can combine them as this one, okay? Now show that f such that R3 maps to R. It means that I'm going to pick a vector in R3 and then whatever value I'll get or whatever definition of f will transform my vector in R3, a three-dimensional vector, to just the real number, okay? And the definition or defined by the definition of f is defined as picking the vector with input x, y, z will should be equal to 3x minus 2y plus z. So what it means is if I pick, let's so an example of this transformation is if I pick you're supposed to show that this is linear, but this is not part of what you're going to use, but this is an example, okay? I'm trying to show an example that if I pick a vector, say let me call this vector little v, which belongs to R3, and then little v is defined to be the vector 1 0 0. Okay, this is an R3 vector, right? And what it means is if I apply f on this little v, it's the same as applying f on the vector 1 0 0. And what it is telling us is we're supposed to do 3 times the x component, which is 1, minus 2 times the y component, which is 0, plus the z component, which is also 0. And this is equal to 3. So this is a real number, right? So it takes a vector as a three-dimensional vector and then gives us just a value in the real as a real number or just a straight value, okay? So that is an example of what this transformation f is doing. Right, so to show this one, we need to show that f of v, let's say as a vector, let me call it, I mean we can call it anyhow. Let's say u1, where u1 and u2 are both vectors in R3. So u1 plus u2 should be equal to f of u1 plus f of u2. Okay, sorry, f of u2. So what these are, the bar, you can put it at the top or the down or the bottom depending on what you are used to. Okay, so these are vectors. So first we have to define u1 to be equal to the vector with component x1, x2, or maybe y1, and then z1. Okay, and then u2 should be equal to x2, right? Remember, x1 and x2 are different, y2 and z2. So you can think of it as u1 to be, so an example of u1 can be, let's say 1, -1, 0, and then u2 can be equal to, sorry, this is u1, can be equal to maybe -1, 0, 1, right? So you can, these two things are different. Okay, so that's what I mean by u1 and u2. You can pick actual examples, but we have to do for all of them. So if you're able to do it for just u1 and u2 as arbitrary x1, y1, z1, and then x2, y2, z2, then it will work for everything. Okay, so that's why we normally choose these things. Then f of u1, let's first do u1 plus u2. Okay, u1 plus u2 should be equal to summation of two vectors is summing the component. Okay, y2, z1 plus z2, right? So what are we going to do? We are going to do this. We are going to take f of u1 plus u2, right? And that is equal to what? F of u1 plus u2, this is u1 plus u2, and then f of u1 plus u2 is going to be f of what we have here, f of the whole of this. So it's going to be f of x1 plus x2, y1 plus y2, z1 plus z2, right? And what is the definition of f? It's going to be 3 times the x component, or the first component, minus 2 times the y component plus the z component. Here the x component we have here is the whole of this summation. Okay, so it's going to be 3 times x1 plus x2 minus 2 times the y component, which is y1 plus y2, plus the z component, which is z1 plus z2. Okay, let me erase these and sorry. Okay, let me rewrite them. So we have 3 times the x component, which is x1 plus x2, plus, oh sorry, it's minus actually, minus 2 times the y component plus z1 plus z2. Okay, that's the z component. So this is the z component, this is the y component, and this is the x component. If you look at a three-dimensional thing, the first one corresponds to the x, the second corresponds to the y, and then the third. So this is what we have for f of u1 plus u2. So when you sum them first and you solve, this is what you have, right? So you can keep this somewhere, and then we'll come back to it later. Okay, now if I do f of u1 was defined to be x1, y1, z1, right? And this is going to be 3 times the x component minus 2 times the y component plus the z component, right? And then f of u2 is also going to be f of x2, y2, and then z2. Okay, that's the definition of the function. And this is going to be 3 times x2 minus 2 times y2, sorry, plus z2. So this is how the individual transformations look like, because the function is defined to be f of x, y, z to be equal to 3x minus 2y plus z, right? So what it means is 3 times the s component, which is here in the u1, the s component is x1, the y component is y1, and then the z component is z1, right? Likewise, for the u2, we have x component to be x2, y component to be y2, and then z component to be z2. So when you do the individual transformation, this is what you get, right? And here, notice that f of u1 plus f of u2, what would you get? You're going to get the summation of these two things. Sorry, let me right? The f of u1 first. That gave us 2y1 plus z1, and then f of u2 gave us 3x2 minus 2y2 plus z2. Now we can try to group the x and then the y component. I have 3x1 here, 3x2, so I can pull out 3 or factor 3, and then I'll get x1 plus x2. I have minus 2 in front of the y, so I can have minus 2 y1 plus y2. And then the z component, I have it like this. But wait a minute, what was f of u1 plus u2? It gave us 3 times x1 plus x2 minus 2 times y1 plus y2 plus z1 plus z2. And if you look at this f of u1 independently plus f of u2 independently, this is what we get. We get the same thing as what we had. So we have this to be f of u1 plus u2. This is what we have. So it means that the first condition that says we should make sure that f of the summation of any two of them should be equal to the the individual transformations, and then you sum them, right? This is checked because that's what I wanted to show. I wanted to show that f of u1 plus u2 is equal to f of u1 plus f of u2, and that is checked now. Okay, and the next thing to check is to show that let me just show it here. F of some alpha times u should be equal to alpha f of u, right? Where u is any vector that you can think of in R3. All right. So what is we are going to do? We are going to do the same thing as in define u. Your vector is a 3-dimensional vector, so you can choose just x, y, and z, because this time around we don't have any two different vectors where we are supposed to separate them with indices like we used to have earlier. Earlier we had two vectors, so we had to denote one of them by x1, y1, z1, and then the other two with that. But here we are just looking at any general vector, so we can choose x, y, z. Okay, so having this, then what is alpha u? So if you have a vector and then you multiply that by alpha, it's going to be alpha x, alpha y, alpha z, right? What is f of alpha u? That is going to be remember, f is defined to be this 3x minus 2y plus z, right? So it's going to be f of what is alpha u? Alpha x, alpha y, alpha z. This should be equal to 3 times the x component, so 3 alpha x minus 2 times alpha y plus alpha z. And this, if I pull out alpha, I'm going to have 3x minus 2y plus z, right? But remember, what is f of u? F of u is the same thing as the transformation that was given, okay? It's going to be 3x plus, 3x minus, actually. Okay, 3x minus 2y plus z, right? So with the f of alpha u, what is this part? This part is giving us the same thing as we have here. So this means it's equal to alpha times f of u. And that's what I wanted to show. I wanted to show that alpha times f of alpha times u should be equal to alpha times f of u. And that one too is satisfied, right? So indeed, the transformation given here is linear. And summarizing everything, when you have a problem you want to solve, you may not necessarily define these things as I have here. You can define this individually like this, and then when you are done and you are so confident, then you can write a proper summary. Okay,